Hello everyone and welcome back to Physical Geology at West Valley College, and I'm your professor Farida Baksa Musa. Today we'll take a deep dive, pun intended, into how Earth's surface is constantly changing through weathering and erosion. This isn't just about rocks breaking down. It's about the foundation of landscape, soil for food, and even how our planet's climate is regulated. So grab your notebook, get comfy, and let's get started. Let's start with a big question. What is weathering? Simply put, it's the process that breaks down rocks once they're exposed to Earth's surface conditions. Things like sun, rain, glaciers, freezing temperatures, oxygen, and living organisms. Most rocks form deep underground. Think high temperatures, huge pressures, and not much change. But when those rocks are eventually brought to the surface, everything changes. Suddenly, they're hit with temperature swings, water from rain or rivers, oxygen, carbon dioxide, and even the roots of plants and activity of animals. This exposure is what unleashes the process of weathering. I always like to tell my students, why do we study this and why should we care? So here's the reason. Weathering is the beginning of soil formation, the source of sediments that make beaches and valleys, the process that releases nutrients for plants, and a key player in the rock cycle that connects mountains, rivers, oceans, and even the air we breathe. So before we zoom in on weathering, let's connect it to the bigger picture, the rock cycle. Very important, a never-ending process that moves rocks from different forms. And in science, everything continues, right? It's a cycle. We've done the water cycle. Let's talk about rock cycle. Deep underground, heat and pressure transforms any rock into metamorphic rocks. We're going to study more about metamorphic rocks later in the coming chapters. The rock can melt into magma. If the magma cools slowly underground, it forms, we've studied that, intrusive igneous rocks. If it erupts, it forms volcanoes. Cools quickly, it forms volcanic or extrusive igneous rocks. Surface rocks face weathering and erosion, breaking down into sediments. Sediments is then transported and deposited by water, wind, or ice, later becoming sedimentary rock. Again, we'll study that in the next chapter through burial and cementation. Any of these rocks can be uplifted, buried again, or melted, keeping the cycle going. Weathering and erosion are the crucial processes that start the cycle all over, breaking rocks down and setting them on their next journey. Let's talk about types of weathering. First, mechanical weathering, also called physical weathering, is when rocks break into pieces without changing their chemical composition. Let's break down the main agents. Pressure release or exfoliation. When overlying rocks are eroded away, pressure drops and the rock expands, causing layers to peel off like onion skins. This process is called exfoliation. With granite in mountain ranges often shows this with rounded sheeted surfaces. If you've been to Yosemite National Park, you'd see beautiful onion rings. I will link the location of the hike here. I recently went to Yosemite and it was beautiful. Frost wedging and frost heaving. Water seeps into the cracks of rocks. When it freezes, it expands about 9%, prying the cracks open further. With frequent freeze-thaw cycles common in places like Canada, cold weathers, the effect repeats, widening cracks and causing blocks to break off. This creates talus slopes, a pile of rock debris at cliffs. Frost heaving happens in soil. Ice forms below the surface, lifts up the soil and damages roads, sidewalks, and fields every winter. Third, salt weathering. In areas with evaporation like shorelines or deserts, salt water enters cracks. When the water evaporates, salt crystals grow, prying grains apart and weakening the rock. This is common along rocky coastlines and even inland where salty soils exist. Fourth, plant roots and animal activity. Roots grow into even hairline cracks, exerting pressure as they expand, breaking apart rocks over time. Burrowing animals like groundhogs and earthworms churn up soil and expose fresh rock to further weathering. While mechanical weathering creates tiny pieces, chemical weathering actually changes the minerals inside the rocks. So let's talk about chemical weathering. Formation of carbonic acid. Rainwater absorbs carbon dioxide from the air, making weak carbonic acid. When it seeps into the soil, which has even higher carbon dioxide, it becomes a bit more acidic. This acid reacts with many minerals, especially feldspars, altering them. So there's a chemical equation, H2O plus CO2 gives you carbonic acid, which is H2CO3. Second type of chemical weathering is hydrolysis, changing feldspar to clay. The most abundant mineral in Earth's crust, feldspar, is altered during hydrolysis. Acidic water reacts with feldspar, producing clay minerals and dissolved ions like calcium, sodium, or potassium. The result? One piece of granite can weather into clay minerals, quartz grains, and ions in water over thousands of years. Oxidation, making things rust. When iron-rich minerals like olivine and biotite meet oxygen and water, the iron oxidizes, turning rocks reddish or brown. Like, think of rusty metal. We've seen this. This is why many rocks change color at the surface. Pyrite, which is FeS, iron sulfide, when exposed during mining, can oxidize to form acidic drainage that harms ecosystems. Fourth type of chemical weathering is dissolution, minerals dissolving away. Some minerals like calcite, main component of limestone, are particularly soluble. They dissolve in acidic water, releasing calcium and bicarbonate ions. Over time, this leads to the creation of caves, sinkholes, and disappearing streams in areas with lots of limestone, a process called karstification. So quartz, the chemical weathering is quartz grains, feldspar is clay, sodium, potassium, Ca2, olivine, there's serpentine, there's Fe2, Mg2, pyrite, iron oxide, and sulfuric acid. Calcite is Ca2 plus bicarbonate HCO3 in solution. Climate has a huge effect on weathering. Warm, wet climates promote intense chemical weathering, thick, clay-rich soils. Dry climates promotes mechanical weathering, dominates, right? Lots of physical breakup, little chemical change. Cold climate, mechanical frost action is strongest, right? Freeze and thaw movement, breaking of rocks. Chemical reactions are slow due to low temperatures. Even within a single region, elevation and slope can have big impacts. Faster water erosion on steep slopes, faster soil loss unless protected by plants. Plants are therefore very good for controlling erosion. Weathering creates loose material, but erosion is what moves it. Here are the main agents. First, water. Rivers and streams cut valleys, transport enormous volumes of sediment and deposit them in deltas, lakes, and oceans. Ice. Glaciers, very dense, they create lots of weathering. Glaciers scrape away the huge landscapes. Think about big boulders that you see. Probably glaciers got a long time ago. Grinding, especially when you climb Mount Shasta, you go to the summit and you'll see a lot. Grinding rock beneath them into fine rock flour and carrying huge boulders far from their source. Wind. In deserts and dry plains, wind lifts sand and dust, creating dunes and stripping nutrients from dry, exposed soils. Gravity. On steep slopes, gravity pulls loosened rocks down as landslides or rock falls, a process called mass wasting. Erosion continuously removes the products of weathering, exposing new rock for more weathering. Without this, mountains would quickly flatten and valleys would fill in. What do we get from all this breakdown movement? We get quartz grains, right, resistant to chemical weathering. Make up much of sand on beaches and deserts. So that's all part of the weathering. The cliffs get weathered from the sand, and it's deposited, transported, and comes to the beach. Clay minerals made by chemical alterations of feldspars and other silicates. Rock fragments, larger pieces from boulders, from gravel to boulders, mainly by physical processes. Dissolved ions, washed into rivers, lakes, and oceans, where they can eventually form new minerals or participate in biological cycles. These materials make up the sediments that build new sedimentary rocks over geologic time. The characteristics, size, shape, and makeup of the sediment tell us about the weathering and transportation history. Soil is essential for life. To a geologist, soil is more specific than just dirt. It's the uppermost layer, rich in organic matter, minerals, water, and air, capable of supporting plants. So let's talk about soil composition. 45% is mineral, mostly clay and quartz. 5% organic material. 50% pore space, air and water. And what affects soil development? Of course, climate, warm and wet, faster formation, clay-rich soils. Too much rain leaches nutrients, too little gives salty or stony soils. The parent material, what is it made up of? Granite gives sandy soils, basalt is nutrient-rich, shale forms clayey soils. We've learned about all these. We will learn about these sedimentary rocks, shales, but we've studied about granite and basalt. Slope. Gentle slope allows soil to accumulate, steep ones lose it. Time. Soil formation is slow, thousands of years, especially after glaciers retreat, they go away. Soil horizons layers develop as water carries material downward. O layer, topmost layer, is organic, extremely rich. A, after that, is topsoil, mix of minerals and organics. E is the leached layer. B is the subsoil, that's accumulated material. C, partially weathered rock. Some arid soils develop a calish horizon, a rock hard layer of calcite from pre-precipitated calcium. Healthy soils are usually balanced. Formation is equal to erosion. But human activities can throw this off. For example, deforestation, right? We said plants are important to avoid weathering. Removes root, anchors and leaf litter, leaving soil bare and vulnerable. Farming and tillage exposes soil to wind and water. Even light tilling moves soil downslope, increasing loss over years. Overgrazing reduces plant cover, making soil prone to blowing and washing away. Water erosion is worsened on slopes and after rainstorms, with sheet wash and deep gullies removing huge amounts of soil. Wind erosion strips exposed fields, turning valuable soil into dust clouds. Once soil is lost, especially the fertile upper layers, regeneration can take centuries. Soil conservation and responsible land management are critical for agriculture and healthy ecosystems. Now let's talk about the big picture, how weathering connects to the global carbon cycle and climate. Chemical weathering of silicate rocks removes carbon dioxide from the atmosphere, turning it into dissolved ions that are eventually reintegrated into rocks in the ocean, a crucial long-term sink for carbon. Volcanic activity and fossil fuel use release CO2 back into the air. For millions of years, these inputs and outputs were roughly balanced. Mountain building like the Himalayas can speed up weathering, drawing down atmospheric CO2, cooling the planet over millions of years. Today, burning fossil fuels is adding CO2 much faster than weathering can remove it, causing our current climate crisis. Weathering is slow, but it's essential for keeping our climate in check until we overwhelm it with rapid large-scale emissions. Keep exploring and remember, every grain of sand, every handful of soil, every landscape you see is a story written by weathering and erosion. And hope you can solve, hope your quizzes go great. If you have any questions, come to my office hours, send me an email, and I'll see you in the next chapter on sedimentary rocks. Bye-bye.